pulsating radio source, a pulsar for short, beats out this rhythm far away among the stars. It's a star utterly crushed by the force of its own gravity. In the thousands of years for which men have wondered about the meaning of what goes on in the sky, there's never before been so dramatic a period as this. When the pulsars turned up just over a year ago, the Cambridge radio astronomers who discovered them were so astonished that they labeled their first records of these regular pulsars LGM. That stood for Little Green Men. It seemed at first less incredible to think that intelligent beings elsewhere in the universe were trying to get in touch with us than to imagine that a star could produce this jazzy rhythm. The pulsars are just the latest in an extraordinary series of discoveries made in the past few years. All over the world, astronomers have spotted events of breathtaking violence, scarcely explicable in the known forces of nature. They are also on the brink of establishing for the first time the history and fate of the universe we live in. That's why we've invited you tonight to come with us around the world. We shall visit the great observatories and meet the astronomers who've opened new windows on the universe and who are making the major discoveries. Our story also involves a Japanese teacher of classical guitar. A huge tank full of dry cleaning fluid a mile underground in a gold mine. An astronomer who flies a telescope 10 miles up. A strange-looking horn that's said to have picked up an echo of the Big Bang with which some say the universe began. In England, they think they've found a horizon of time before which the universe had no stars. This American foresees that the heavens will truly fall one day and bring our universe to an end. In a way, it was this Dutch astronomer, living with his family in California, who started the present revolution in astronomy. Martin Schmidt was the first man, 6 years ago, fully to realize the violence of which nature is capable. He's just setting off for Palomar Mountain, where he'll use this giant telescope to gaze across the oceans of space and time. Later, we'll join him there. We're not only going round the world, we'll be traveling out into the great void that starts just above our heads, to the storm-swept sun, out among the stars to see their violent births and even more violent deaths, to distant galaxies, vast collections of stars like our own Milky Way. Incredibly enough, galaxies sometimes explode. And going on, out as far as the human eye can see, we'll examine the evidence that the universe itself began with a Big Bang. You and I are products of the forces of nature, operating over thousands of millions of years. The upheavals which astronomers speak of are creative as well as destructive. We are children of a violent universe, and that's why what happens among the stars is a matter of intimate interest to us. This is the golden age of astronomy, and tonight the astronomers want to share their excitement with us at a rare moment of discovery such as may never occur again. And to help guide us among the new discoveries around the world of the astronomers and through this vast universe, we have with us Carl Sagan from Cornell University.
Our sun is a star. It seems large because it's so close, but for all that, it's a humdrum and quite ordinary star. We've modeled the sun and the nearby stars. Here, this star that's blinking is our sun. Near it are the neighboring stars in space. Because of our vantage point near the sun, we're able to recognize the familiar constellations of the night sky. To the north, we can see the Big Dipper pointing towards the pole star. Near the Milky Way, we can see the familiar winter constellation Orion. If you live in the southern hemisphere, you'll recognize the Southern Cross. Let's take a stroll among the stars. Let's amble north. As we do so, let's keep an eye on the Big Dipper. Notice how its shape seems to change as our perspective changes. The reason is that the Big Dipper is composed of stars, some of them intrinsically bright, but rather far away, some dimmer, but closer in. The constellations that seem to be points of light painted on the vault of the heavens are really composed of stars at a variety of distances. And if there are creatures that live on planets of other stars, they will see different constellations in the night skies than we do. Well, we've reached a star which astronomers call Gamma Cephei. It's so far from the sun that it takes light some 50 years to travel from the one to the other. The earliest signals of our technical civilization on the Earth are only just now reaching Gamma Cephei. These signals are the earliest radio broadcasts, perhaps an aria of Enrico Caruso, but we do not know if there's anyone here to listen. Let's take a look back the way we've come. Let's try to see if we can recognize where we've come from. Which of these stars is the sun? The sun is such an insignificant star that we can't make out which of all these stars it is. In fact, the only way we can do that is to ask it to blink for us. Blink, sun. There it is. We can now amble back towards home. As we do so, we can recall that these points of light in the sky, every one of them is as mighty a star as our sun. Let's head home to our familiar solar system. As we do so, we can recognize the planets accompanying the sun. Looming up is the giant planet Jupiter, a gassy planet very different from the rocky and metallic Earth. As we move inwards from Jupiter towards the sun, we can make out the red planet Mars, a possible abode of life, the target of 2 American space vehicles now on their way to explore Mars. If we continue further inwards towards the sun, rapidly passing by our home planet, we reach Venus, a cloud-covered planet with a searing hot surface. At the present time, there are 2 space vehicles launched by the Soviet Union which are headed towards Venus, perhaps to land there. Let's now return to our comfortable and cozy home planet, the Earth, with its tiny moon which circles it.
This is the year of Apollo, when men may first set foot on the moon. It's an extraordinary enterprise, a first step into the universe. But distances in the universe are so vast that they're often reckoned by the time light takes to cover them, at 186,000 miles a second. The moon is a little more than 1 light second away, and light from the sun takes 8 minutes to get here.
In our little excursion among the stars, we traveled a total equivalent distance of perhaps 100 light years. Later on in this program, we'll be concerned with immensely greater distances, distances of billions of light years. Compare that with the tiny 1 1/3 light seconds between the Earth and the moon. Astronomers worry about 2 very large questions. How does the universe work, and where did it come from? In this program, we consider both these questions on the nature and the origin of the universe. The first question is an attempt at understanding what we see in the sky in terms of known natural laws. Why does the sun shine? How do stars evolve? What's the explanation for these extraordinary cosmic explosions which astronomers are detecting with appalling regularity? The second question is an even deeper one. Is it possible that the universe was made instantaneously from nothing at some remote epoch in the past? This is the view taught by Babylonian astronomers, and it's familiar to us from Genesis 1:1. Its modern astronomical version is called the Big Bang Theory. Or is it possible that the universe had no beginning, that it's infinitely old, as some Oriental religions teach? One modern astronomical version of this theory is called the steady state theory. We consider both these theories later in the program. We begin with the forces of nature and how they work in the stars. We'll encounter 3 principal forces. The force of gravity, which holds stars together and keeps their insides hot. Nuclear forces, which produce starlight in the insides of hot stars. And magnetism, which in a way is the least potent of these forces. And yet, look at this soaring, awesome surge of hot gas rising some tens of thousands of miles above the sun, guided by the sun's gravity, by the sun's magnetism. In this picture, this tiny circle represents the size of the Earth. It's to scale. In a way, it's a lucky thing that we're not this close to the sun. To further examine such disturbances on the sun, we go first to a unique observatory in Australia.
At Kalgoorlie, in the outback of New South Wales, a remarkable new telescope watches the sun. 96 dishes deployed in a 6-mile circle operate as one huge instrument, collecting the radio noise that tells of the violent explosions on the sun. Radio telescopes have a particular knack of picking out violent events in the universe. The reason is that hot blasts of gas caught in magnetic fields make powerful natural transmitters of radio waves. Many of the radio sources in the sky are extremely far away, but the sun is the nearest place in the universe where astronomers can see natural forces at work with a ferocity quite unknown on Earth. The radio noise comes from high up in the hot atmosphere that surrounds the sun. The surface layers of the whole continent of Australia could be blasted from here to the moon if the force of the greatest explosions on the sun were let loose on Earth. These flares, as they're called, also provoke outbursts of radio noise. 200 miles of wire carry the information about the weather on the sun from the circle of dishes to the electronic heart of the telescope. There they disclose the state of the sun's atmosphere in a motion picture. The circle represents the sun as you and I see it. The bright patches above it are radio outbursts. This unique instrument was conceived by Paul Wild.
When we were building this telescope, we had no very clear idea what to expect in the way of results. You see, we've been studying the radio waves from the sun for many years, but always by indirect means. And the thing that we really wanted all the time was to get radio pictures of the sun. And now, at last, we have radio pictures of the sun, and the first year's results, in fact, have been very rewarding and given us a lot to think about. The sun is pretty active at the moment, but the first really interesting result that we got occurred on February the 25th, 1968, at 4 hours Universal Time. The bright patch there is a radio burst which occurs immediately above a visible solar flare. The flare had started some minutes earlier. The radio burst was actually caused by a shock wave travelling upwards from the centre of the flare at a speed of about 1,000 miles per second, eventually reaching the height where its radio waves are generated. Now a second burst occurs more than 500,000 miles beyond the edge of the sun. This happens immediately above one of those rising arch prominences. This prominence had been triggered into eruption by the arrival of another part of the same shock wave, this time travelling across the face of the sun. This record quite clearly demonstrates how one event on the sun can trigger another, even though they are separated by 1,000,000 miles. This new technique of being able to photograph what is going on high above the sun should help us disentangle many of the problems associated with the activity on the face of the sun. In particular, I'd like to know the basic cause of flares, which are by far the most violent events in the whole of the solar system.
In Arizona, at the Kitt Peak National Observatory, astronomers trace the origins of flares to the visible face of the sun. The most powerful optical telescope, specially made for solar work, stands like a great sundial on the mountaintop. The biggest flares on the sun flood the surroundings of the Earth with atomic radiation, which may be a danger to astronauts and even to passengers in high-flying supersonic aircraft. On top of the tower at Kitt Peak, a flat mirror tracks the sun as it moves across the sky and casts its light into a tunnel. The tunnel slants down for 500 feet to the big reflector embedded deep in the mountainside. The sunlight, now focused, returns up the tunnel to the observation room, where it forms the largest image of the sun available for study by astronomers anywhere. The most conspicuous signs of storms on the sun are dark sunspots. As the spots sweep across the large black hole, detectors register strong magnetic forces in their neighborhood. Magnetism in the sun's atmosphere above a sunspot is recorded by this pen. At 93 million miles range, the sun betrays its stresses. Here's how the trick is done. Beneath the ordinary-looking tabletop is a 65-foot spectrograph, which finely grades sunlight by its colors and wavelengths. Magnetism at different levels in the sun's atmosphere reveals itself in subtle effects imprinted on light of particular wavelengths. From the data recorded point by point across the face of the sun, the astronomers can have charts made up. The mosaic reveals a jungle of magnetic zones and the strong fields of the sunspots. Magnetic contortions around the sunspots cause energy to build up, the energy that suddenly bursts out in a violent flare. The colors of the mosaic indicate the strength and direction of the magnetic field at each point. And it's between close pairs of zones, shown by contrasting colors, that a magnetic loop can form, which propels the stuff of the sun high above the surface to make these extraordinary prominences. The surface fireworks of the sun are very impressive, yet the magnetic energy involved is almost insignificant compared with the nuclear energy at the heart of the sun. Machines called accelerators show on a minute scale how nuclear forces work in the sun and the stars. William Fowler of the California Institute of Technology is a pioneering investigator of the nuclear life of stars.
The observational astronomer works at the telescope. The experimental nuclear physicist, like myself, works at the accelerator. I think it's fair to say that we've learned as much about stars at the accelerator as we have at the telescope. Here in this laboratory, we study the nuclear processes that take place in the sun and in other stars. These processes generate the energy with which the sun shines. All of the light and heat that has fallen on the earth from the sun was originally generated deep in the sun's interior. This energy generation takes place through the transmutation of the element hydrogen into the element helium. Nuclear processes not only create energy in stars, they create new elements. Turns out that in other stars, and eventually we think this will happen in our sun, helium is being converted into carbon and oxygen, these elements into silicon, the silicon into iron, and all the way up through the chemical periodic table to uranium and the transuranic elements. As a matter of fact, we think this is the way all of the elements heavier than the primordial hydrogen were created. This includes the elements in the earth and in your body and in mine. All were formed in stars which were born, evolved, aged, and died a violent explosive death long before the sun and the solar system came into being. Now, there's some uncanny things in this chain of element synthesis. One of the atomic nuclei in the chain, beryllium-8 by name, is slightly unstable. Had it been stable, the whole chain of element synthesis would have been quite different than it actually was. And the delicate balance between the abundances of the element carbon and oxygen and the still heavier elements that were necessary for the formation of life as we know it here on Earth would just not have occurred. we would not have been here. Now, we think we can account for all of the chemical elements, why iron is common, and why gold is rare. We think we know why stars can shine steadily for thousands of millions of years and then violently explode in what astronomers call supernovae. But we would like to have more direct evidence of what's taking place in stars, and in particular in the sun. That evidence is now being sought in a most unlikely place.
It's nearly 100 years since the gold rush of '76 hit the Black Hills of Dakota. Calamity Jane and Wild Bill Hickok today lie buried over the hills in Deadwood, South Dakota, and the surface gold that lured the adventurers has long since vanished. But here at Lead, the miners are still encamped. They follow the run of the precious ore far underground. It's the biggest gold mine in the Western Hemisphere, Homestake. The graveyard shift is just ending.
Hi, Doc. You caught any little stranger down there?
Wish I had.
Raymond Davis, a chemist from the Brookhaven National Laboratory on Long Island, does his astronomy in the depths of the mine. Just one assistant goes down with Davis to the underground laboratory. No sunlight reaches a mile underground, nor do X-rays from the sun, nor even the atomic bullets of the cosmic rays. No radiations pass unhindered through such a roof of rock. Nothing, that is, except the most ghost-like of rays, which are called neutrinos. They breeze right through the Earth.
Ray, if you'll take these, I'll turn the cooling water on. Okay.
100,000 gallons of dry cleaning fluid fill this tank to catch neutrinos coming from the very heart of the sun. The neutrinos are so elusive that other rays would swamp any detector. That's the reason for taking refuge with the gold miners. But though they're hard to detect, there is a way. Some neutrinos do react with atoms of chlorine. The liquid in the tank is mostly chlorine. As vast numbers of neutrinos stream through it day and night, a few react with heavy atoms of chlorine. Every 3 months or so, Ray Davis comes to Homestake to gather a harvest of neutrinos. More precisely, he collects the atoms that have stopped neutrinos. That interaction changes the chlorine atoms into a radioactive gas, a form of argon. In his underground laboratory, Davis prepares to extract the argon atoms. A trap cooled with liquid air is part of the system for collecting the telltale argon. Helium gas roars through the tank, sweeping out any trace of argon. When the gas stream circulates to the laboratory, this cold trap freezes out any vapor that's mixed with the gas as a first step in purifying the argon. It's a week's work purging the tank of its traces of argon. The cold traps have done their work of collecting and purifying the argon gas. Now it's been released from the last trap. Pressure of mercury shunts the gas through the pipework. The gold miners along the tunnel digged several tons of ore to win an ounce of gold. Similarly, the purified yield from the huge tank is a little argon gas containing a very few radioactive atoms that tell of neutrinos caught during 3 months' watch on the sun. The radioactivity will be measured in Davis's home laboratory, 1,500 miles away on Long Island.
When we designed this experiment, we expected 5 to 10 neutrinos to be captured in this tank every day. Our measurements so far show that less than 1 day. So this means that the center of the sun is not as hot as we thought it was. Maybe it's 1,000,000 degrees cooler than we thought.
You know, Ray's tank is really a gigantic thermometer with which he's taking the sun's temperature. So far, he's told us that the patient's temperature is less than what all we doctors thought. But we don't think we're going to have to change our general ideas of the structure and the nature of the sun. We think if Ray improves the sensitivity of his equipment, he'll find the neutrinos all right. But I have to confess to you, we've got our fingers crossed.
For astronomers, the sun is conveniently near for examination, whether they're looking for neutrinos from its center or watching the magnetic upheavals on its surface. This unusual picture of the sun was taken from a rocket by a company called American Science and Engineering. The bright spots are stormy regions that are emitting X-rays, intense rays that are stopped by the air, so that you have to get your camera above the atmosphere to take such a picture. Looking at the sun helps astronomers to understand much more distant stars. But by looking out at other stars which come in all sorts of sizes and conditions, young and old, hot and cool, astronomers can work out the history of our sun.
This is a cluster 10 billion years, twice the sun. Some of them are colored red and have enormous dimensions. They're called, for this reason, red giants. When our own sun is about the same age, it will have exhausted much of its available nuclear fuel in its interior, and it also will become a red giant. Its outer layers will expand, it will become distorted, distended, it will engulf first Mercury, then Venus, and eventually our own planet, the Earth. Our oceans will boil, our atmosphere will dissipate to space, and it's interesting to ponder whether our remote descendants, if any, will be equal to the supreme challenges of such times. But fortunately, this is all several billions of years in the future. Red giants blow their outer atmospheres off into space, forming a kind of cosmic smoke ring, like this. The remainder of the star then collapses, contracting to form an extraordinary kind of object called a white dwarf. Actually, red giants and white dwarfs are part of contemporary astronomy and not something from the Brothers Grimm, as it might sound. A white dwarf is something so dense that a teaspoonful of it would weigh a ton. The initial energy of gravitational collapse heats the star so it's white, but it has no other fuel supplies to draw upon, and it gradually cools, ending up its days as a cold, black, dead ember, little bigger than the Earth.
We turn now from the death of stars to the birth of stars. But let's be clear about the arena in space we're dealing with now, the Milky Way. You see it as a band of light across the sky, but in fact, It's a vast collection of stars, a galaxy, of which our sun is a member. There are at least 100 billion stars in the galaxy. Looking even farther out, astronomers see other galaxies as big as our own, dispersed like ships in the ocean of space. Here's one very like our own. If we could look at the Milky Way from the outside, it would appear as a spiral like this one. Or, looking sideways on, that is where the sun and Earth are. There, out to one side. But in fact, we look from the inside and see the flattened disk of stars as a streak across the sky, all around us. The view is obscured, even to powerful optical telescopes, by clouds of gas and dust that lie in the disk of the Milky Way. Radio telescopes give a better impression of the distant part of the galaxy, and of how, out of clouds like these, new stars are forming. According to mythology, the stars of the Milky Way were spilt across the sky from the breast of a nursing goddess, Juno herself. Not all that milk has yet formed its stars. The great telescope at Parkes in Australia is mapping the Milky Way by radio, and the modern painting shows the regions rich in gas, which are still capable of making new stars. The existing stars don't show up on the map, only the thin hydrogen gas lying between them. This gas broadcasts its own characteristic radio waves, which pass through the dust that obscures the starlight from distant regions. Radio astronomers can work perfectly well in daylight. The 210-foot dish at Parkes turns towards the Milky Way.
Start the scan, please, Ben.
As the telescope sweeps the Milky Way, it records strong radio waves from particular regions. In this case, a section of what is called a spiral arm. Our galaxy, like many others, turns out to have spiral arms wound around the center. As mapping continues, the pen recorder gives the astronomer an impression of what the telescope is picking up, a cross-section of the Milky Way.
Inclination minus 51 degrees.
The details are recorded in a form which a computer can read. The milk of the mother goddess is registered as a code of holes, punched in a tape. The computer is the map maker. It plots the radial contours of our galaxy, seen edge-on from our vantage point within one of the spiral arms. The colors bring the disk of the Milky Way to life. The regions of strong signals are those where the galaxy still has the capacity to renew itself in new stars. But before stars can be made, the gas of the Milky Way has to form denser clouds on a relatively small scale. On the other side of the world from Parkes, British radio astronomers at Jodrell Bank seized a new opportunity for detecting small gas clouds. The mysterious pulsars are ready-made beacons lying in the Milky Way, which illuminate the beginning of star formation. Manchester University's giant dish, famous for tracking spacecraft, spends more time exploring the universe. At its focus, the radio pulses are gathered. The antenna arms find waves vibrating most strongly at one particular angle. That's because of magnetism within the pulsar itself. The angle of vibration has been twisted by invisible gas clouds in space. Thus, Graham Smith uses pulsars even without knowing exactly what they are to explore our galaxy.
Our galaxy, the Milky Way, contains between the stars a very thin gas, and we believe it's out of this thin gas that stars are made. It's been very difficult to measure how much gas there is because it is so thin. But the pulsars have given us a marvelous opportunity of doing just this. The radio pulses come through the gas and they act as a sort of probe. We can measure the delay the time it takes for a pulse to go through, and this tells us just the amount of gas there is. Furthermore, we can also measure the size of the clouds. For example, we know that some clouds are about the size of the solar system. And so here we have the gas out of which the stars are made. But there's one problem. The stars have a magnetic field in them, and we know that this magnetic field has been shrunk into the star as the gas clouds shrink into a solid body. We'd like to know how strong the field is before it starts. And again, the pulsars have given us a measurement. The shape of the pulse, detailed shape of the pulse, changes as it travels through the gas. We've been able to measure these shape changes and measure the strength of the field. Now we have then the gas and the magnetic field, and we can begin to understand this basic process of how stars are made out of the very thinnest and coldest gas that we have. Well, let's go to 2015 plus 28. I think I've got a good calibration here.
The Orion Nebula is the best-known maternity ward of stars. It's a cloud of gas and dust studded with brand-new lights. Strange radio emissions and heat rays disclose hidden objects, which are stars in the very process of formation. The force of gravity sweeps up a huge volume of gas and heats it to make a star. The newborn stars come alight and visible to the optical telescopes. They're scrutinized from the Lick Observatory, perched on Mount Hamilton, more than 4,000 feet above the fog of San Francisco Bay. At the great 120-inch telescope at Lick, preparations are made to observe one of the very young, newly formed stars. After 20 years of work, George Herbig is a leading authority on the youngest stars. Tonight he wants to analyze the light of one of them, and this strange room is the camera he will use. Light gathered by the 120-inch telescope is guided into this room at its base. The room is kept sealed and cool, and even the heat of the astronomer's body would distort the delicate optics if he lingered too long. This curved mirror focuses the starlight onto the photographic plate. But the most important device in the system is a grating which breaks up the starlight into its component colors to make a spectrum. From features of the spectrum, the astronomer will deduce what is happening in the neighborhood of the star. The night assistant steers the telescope to the approximate position of the wanted star.
Ken?
Yes, Dr. Kirby?
3 seconds east, please.
All right, 3 seconds.
And the rate, 50 seconds in declination south.
You have 50 seconds in declination south.
All is now ready, and George Herbig, master astronomer, settles to work. The fine adjustments are made by the astronomer himself. All the while, the Earth turns, and the great telescope has to follow the star slowly and precisely, like the hour hand of a clock. The astronomer must keep the starlight falling on the slit of his big camera for as long as necessary to produce the photographic spectrum he needs. Some stars are so faint that they need an exposure of several hours. Notice how the starlight jumps about. This is the twinkling of the star caused by the astronomer's worst enemy, the turbulent atmosphere of the Earth. Seeing is the term they use to describe the degree of turbulence. It is such patient work through long, cold nights that gives the astronomer his authority to explain the workings of the universe.
What fascinates me is that we are now able to observe and partially to understand the violent activity that accompanies the birth of a new star. New ideas have come out of these studies. For example, the idea that our own planetary system is not the result of some later and independent event, but actually came about as a natural consequence of the formation of the sun itself. In fact, we, as well as the Earth, are very probably made of material that was part of the surface layers of our sun. Ken, that position of Fu Orionis was for equinox 1969. What do your dials read?
The dials read 5 hours, 43 minutes, 37 seconds.
Around the young sun, the Earth and the other planets formed. From that task, nature left some unused material, the comets. This one, the most brilliant new comet of the century, was discovered by amateur astronomers in Japan. You don't need a big telescope to spot comets. In fact, small instruments are better because they cover a wider area of the sky. Comet hunting is an ideal job for amateurs. Tsutomu Seki, co-discoverer of the famous Ikeya-Seki comet of 1965, continues his search for others on every clear night. His little observatory is on the roof of his home in Kochi, a small Japanese city. This celebrated astronomer earns his living by teaching classical guitar. Man-made lights are a nuisance to astronomers, especially to Seki, living, as he does, right in the city. He has to wait until everyone else has gone to sleep. Seki saved for 10 years to buy these binoculars. They cost him $800. And by staying up each night until 3 in the morning, Seki has discovered 5 new comets. Comets first appear as faint little smudges, but Seki recognizes them intuitively at first sight. The motion of a comet can be measured from night to night in sky photographs, and Seki uses a homemade telescope for this purpose. A friend ground the mirror for him. In more superstitious times, comets were fearful omens of disasters to come. To modernize, they are the scrap of the solar system, icy dust balls that plunge in from the depths of space and swing around the sun. Their tails are blown out like smoke in a wind of high-speed particles that pours continuously from the sun. Every astronomer has his chosen way of keeping warm on a cold night at the telescope. Seki favors electric slippers. "20 years' experience of finding his way around the sky makes the work easier. He's able to discount the hundreds of other nebulous objects that may be mistaken for comets. As he has no electronic computer, Seki spends 48 hours working out an orbit. Just as he taught himself to find comets and play the guitar, so he mastered the mathematics that he needs. 3 or 4 nights' observations of a comet's movements give enough information to calculate its orbit, as it sweeps around the sun and heads off again into deep space. The astronomer reduces the workings of the heavens to numbers, as men have always done since they first made calendars and tracked the wanderings of the planets. But his heart, as well as his scientific curiosity, is stirred by the wonders of the night sky.
When I survey the bright celestial sphere, so rich with jewels hung that night doth like an Ethiop bride appear, my soul her wings doth spread and heavenward flies, the Almighty's mysteries to read in the large columns of the skies. For the bright firmament shoots forth no flame, so silent but is eloquent in speaking the Creator's name. No unregarded star contracts its light into so small a character removed far from our human sight. But if we steadfast look, we shall discern in it, as in some holy book, how man may heavenly knowledge learn. It tells the conqueror that far-stretched power, which his proud dangers traffic for, is but the triumph of an hour. Thus those celestial fires, though seeming mute, the fallacy of our desires, and all the pride of life confute. For they have watched since first the world had birth, and found sin in itself accursed, and nothing permanent on earth.
Nothing permanent on Earth. There's nothing permanent in the whole universe. We've seen the magnetic upheavals on the sun. We've talked about the nuclear fuel of stars and how eventually it's exhausted. We've seen gravity at work, making new stars. All of these processes far surpass the strongest efforts of natural forces on Earth. But now we must move on to events of much greater violence yet. A star is a large nuclear reactor. But some stars turn into huge nuclear bombs and come to a far more dramatic end than is forecast for our sun in the supernova, which is the astronomer's term for an exploding star. The stars most likely to explode are massive stars, much heavier than the sun, which are very hot. They give off very strong ultraviolet rays, like the ones in the constellation of Orion. Here's another photo of the Orion Nebula, which is an Orion's sword, and which we saw earlier as a breeding ground for stars. It's been taken by invisible ultraviolet light, specially for this program by the Royal Greenwich Observatory. You see young stars burning very hot. But most of this ultraviolet light is cut off by the Earth's atmosphere, which is just as well for us, or we'd be barbecued by ultraviolet rays from the sun. It means, though, that astronomers have to use rockets and satellites to get their telescopes above the atmosphere for a good look at the hottest stars. For 10 years, American astronomers and space engineers worked on a satellite for ultraviolet astronomy. As the most complicated scientific satellite ever built, it cost $75 million, and it finally rose from Cape Kennedy just 4 months ago. The Orbiting Astronomical Observatory, or OAO, carries a battery of 11 telescopes high above the Earth. It's controlled by astronomers on the ground.
Can you load from MacNeil? Roger to that, we see you.
Roger.
Roger, voice. Southcom, we don't see you.
Santiago, OAO. I'm issuing a command to put you in a no-verify mode. Roger. At this time, I'm going to ask you to send back experimental data.
The OAO picks up the ultraviolet light from hot stars, which the atmosphere cuts off from ground telescopes. Opening this new window on the universe demands the complex drills of space flight. Astronomers at the Goddard Space Flight Center peer, in effect, through telescopes high above the atmosphere as the OAO passes over the eastern United States.
How'd the picture look on that one, Otis? Very good. Well, there's camera 1 reading out. We're looking at the sword in Orion right now. The central star is Theta. It's a double star. One star is 5.16 magnitude 06. The other is 5.07095. This is camera 3 right now. It's reversed from camera 1. The star field's down in the lower right-hand corner. It has a different filter on it. Getting ready to read out camera 4 right now. One of the other stars in the field is Iota. It's the one at the very bottom of the field, and it happens to be a 2.77 magnitude 09 star. And that's the end of the readout for our 3 cameras for this pass.
At the Smithsonian Astrophysical Observatory, Fred Whipple and Robert Davis take a census of ultraviolet stars. Their computers catalog 700 a day. This is Fred Whipple.
The beauty of the OAO experiment is that it registers the light in the very far ultraviolet where the huge massive stars, very hot stars, are tremendously bright. And because these stars are very young and have very short lives compared to the sun, because even though they are more massive than the sun, they burn up their fuel at a tremendous rate and therefore have very short lives. Now with regard to these very hot stars with their short lives, they usually end in a supernova explosion which spews out the material into space. And while this process is going on, they make out of hydrogen and helium the heavy elements, like earthy elements, that indeed constitute planets where they are formed in the system. And if it were not for these supernovae, there probably wouldn't be an Earth at all, because in the early stages, this material from such explosions collected into the solar system and produced the material that we're actually standing on here. The OAO, then, is going to be able to study these stellar nurseries in space so that we can find out just how these processes of evolution go on.
Fred Hoyle blows up stars by computer. This cosmic anarchist is the most controversial of theorists.
If you think there's a mystery about why stars explode, then you've got it all wrong. The real mystery is why stars aren't exploding all over the sky. The thing to remember about stars is that they're a battleground between gravitation and nuclear physics. Gravity is trying to pull the stars always tighter together, and nuclear physics is trying to heat up the gas and make it expand apart. When one of these battles is going on, as it is inside the sun now, the nuclear physics always holds its own. But after a time, all nuclear fuels become exhausted. And when they become exhausted, gravity wins. But the point I want to make clear to you, there isn't just one nuclear fuel, there are several. So there is a whole sequence of battles. Whilst the battle is on, nuclear physics is okay. But once the battle is over, gravity takes charge again. So the battles, as they go on, one nuclear fuel after another become more and more extreme. And in the final battles, there is the possibility that the nuclear forces, the nuclear processes, become so violent that they're able to shatter at least a portion of the star. And that is what we see in exploding stars, or supernovae, as they're called.
The wispy debris of a star that exploded thousands of years ago still glows brightly as it expands as a huge shell of gas. The Crab Nebula is the best known of the supernova remnants. It's the remains of a star that Chinese astronomers saw exploding in AD 1054, 915 years ago. Today, the Crab is a mine of information for astronomers. It's mapped by radio astronomers as one of the strongest radio sources in the sky. And rocket telescopes have detected intense X-rays coming from the cloud. One of the puzzles of the Crab Nebula has been to explain how it stays so bright 900 years after the explosion. Although it's one of the most carefully studied objects in the sky, there's one feature everyone missed until just a few months ago. What that dramatic novelty is, we'll come to later on. But here is a star brewing up right now. It's photographed for the first time in color, especially for this program, by the Mount Stromlo Observatory in Australia. This star was seen to flare up in 1843, but now it's warming up again. It's one of the strongest sources of heat rays in the sky. Eta Carini is a puzzle, really. It is less violent than a supernova, releasing an immense amount of energy, but it's doing so in slow motion. Eta Carini is 6,000 light years away. If a nearby star were to explode, it could be very unpleasant indeed. Atomic radiation from the star might force us to shelter underground. It could be like the fallout from a nuclear war, with incalculable effects on life on this planet. In fact, as nearby stars must have exploded from time to time in the history of the Earth, some astronomers think that some of the big changes in life in the past may have been due to atomic radiation from them. As it is, exploded stars far away continue to bombard the Earth with mild radiation, and it's easy to get a hint of that. This is a simple detector of atomic radiation. This radioactive material in the luminous dial of this wristwatch makes it chatter. Take it away, and we still have the odd count. Some of it may be coming from slight radioactivity in this studio, but much of it is due to cosmic rays, high-energy atomic particles coming from the depths of outer space. The latest and best evidence that they come from exploded stars is provided by Peter Fowler of Bristol University in England. He flies big balloons to pick up cosmic rays at the edge of the atmosphere before they're degraded by collision with the air. The balloons carry stacks of high-grade photographic film that records tracks of particles. The cosmic rays include representatives of all the chemical elements. But the most interesting thing is that Fowler finds very heavy elements that don't occur on Earth. The heaviest natural element is uranium, number 92, for the perfectly good reason that very heavy elements break down rather quickly into lighter elements. Here's the track made in the emulsion by the most massive particles so far encountered in the cosmic rays. It corresponds to element number 108, or thereabouts. It must have been made rather recently, and the most likely source is an exploding star, a supernova. Fred Hoyle has said, in general terms, why stars explode in a violent battle between nuclear forces and gravity. But to understand it better, we should look more closely at the life story of a star.
Massive hot stars have a much more dramatic and much briefer life than the sun's. But let's begin by considering the biography of our sun, starting some 5 billion years ago, when it formed out of the mother gas between the stars. Release of gravitational energy makes the star gradually hotter as the material falls in. But that capital of energy does not last very long. The reserves of nuclear energy do not come into play until at the very center, hydrogen begins to react, or burn, as we say loosely, to make helium. Its radiation is produced at the center and wanders to the surface. This is how the sun is now, halfway through its active life. But eventually, it will run out of fuel. At the center, it will begin to burn hydrogen further out and swell into a red giant. Then the center becomes hot enough for helium to react. The star is burning its ashes. It suddenly readjusts itself before starting to grow again. In this phase, the sun will swallow the Earth. It's short of fuel now. The surface layers are then blown off to form what we call a planetary nebula. But the rest of the star contracts to form a very small and hot white dwarf. Burnt out, with no energy supply left, it simply cools down. After billions of years, it simply becomes a pile of dead ashes. Now, let's consider a more massive star. Let's say a star 15 times more massive than the sun. It begins its life roughly the same as our sun does, using gravitational energy to heat its interior. But gravity keeps its insides much hotter. It expands itself 60 times faster than the sun does. And as we'll see, it eventually gets hot enough to make much fuller use of the possible nuclear fuels. The immense heat released originally by collapse under gravity is quite quickly radiated throughout the star. The surface becomes very hot. The star eventually begins burning hydrogen in a large core for most of the star's lifetime. But when hydrogen fuel runs short, nuclear burning of heavier elements begins. First helium, forming carbon and oxygen, which are also burnt. Then neon, magnesium, silicon, eventually forming iron, which can't burn in nuclear reactions. The core suddenly cools, it collapses, and a supernova is produced. The outer body of the star is racked by a nuclear explosion and blasted into space. Astronomers have long thought that what is left at the end of such a nuclear explosion is a white dwarf, that very dense star we talked about before with a density of a ton per teaspoonful. You may think that's dense enough. But it now appears that what may be left at the end of such an explosion is not a white dwarf at all, but a neutron star. A star with the incredible density of an atomic nucleus. It's, in a way, the world's largest atom. It's so dense that an equivalent density would be if you had compressed the Earth into a size about 100 yards across.
To see why ideas are changing fast, we have to take up the story of the pulsar, the pulsating radio sources discovered in Cambridge last year. You remember that beat from the very start of the program? We were then on the island of Puerto Rico, where a remarkable radio telescope operated by Cornell University was picking up a pulsar. It's up here, 500 feet above the ground. Antennae gather the radio waves. To be a member of the very exclusive Pulsar Club, you need a big radio telescope. And here at Arecibo, they have the most sensitive of all. A huge dish 1,000 feet across, carved out of a natural crater. It picks up the beat of a pulsar. At first, all the astronomers could be sure about was that any ordinary star was far too big to produce such sharp pulses. At Arecibo, the pulsar work is led by Frank Drake.
Observing pulsars is like listening to a Beethoven symphony. There is the rhythm of the pulses themselves, and within the pulses, a complicated pattern of notes, sometimes at one frequency, sometimes at another, just as in the melody of a musical composition. All of this gives us clues as to what the pulsars are. Certainly they are very small stars, stars that have collapsed under their own gravitational pull to tremendous densities.
6 months ago, no one could connect the pulsars with any other object in the sky. The break came with this radio telescope, the Mills Cross of Sydney University, sited at Molonglo near Canberra. The antenna arms are a mile long. It quickly outstripped all other observatories in its tally of pulsars detected. But one of the earliest it picked up was exceptionally important. It was also the first success of the ace pulsar hunter, Michael Large.
I usually come to the site here from Sydney, a distance of 200 miles, by car. And on one occasion, as I was driving down, I had a very strong hunch that I should set the aerial to declination -46. These charts run for a period of 3 hours. And to avoid losing a minute of possible observing time, I set up a bed in the laboratory and woke myself up every 3 hours. It's terribly difficult getting to sleep when you know you're going to be roused in 3 hours' time. I did this every night, and I was observing in the day too, of course, for 2 complete days and nights. And by the end of that time, I was feeling desperately tired. I felt as if I'd been at it for 2 weeks. And then, about 7 o'clock one morning, just before breakfast, I discovered this record on the chart recorder, my first pulsar. I was cock-a-hoop about this, and without further thought, I rang up Professor Mills, my boss, in Sydney and told him about it. He was pleased, of course, but later on in the day, he rang me up wildly excited. I hadn't realized it, but this pulsar of mine was situated very close to the center of a supernova.
Bernard Mills in Sydney immediately passed the news to Tommy Gold at Cornell University.
I, too, was wildly excited when I heard of this discovery. Mills sent me a telegram. Here was the connection between supernovae and the pulsars. A most important connection, which became even clearer when the 300-foot dish at Green Bank in West Virginia picked up pulses from the direction of the Crab Nebula.
The big dish at the National Radio Astronomy Observatory detected a pulsar among the remnants of the exploded star, but it couldn't track it to measure its pulse rate. The Green Bank astronomers asked their colleagues with the 1,000-foot telescope at Arecibo to lend a hand. The radio astronomers at Arecibo had their own program for hunting pulsars. They quickly switched it to the pulsar in the Crab Nebula. Records of the radio emissions from that part of the sky were analyzed. The pulsar was plainly much faster than any discovered before. That in itself was highly significant.
Well, John, here's one that looks fairly reasonable.
What are you trying to sell us this time, John?
Well, this one is in the right place on both the channels, and it doesn't show the interference spike, which would be over about here if this was nothing more than interference.
Which is the high channel here, John?
The high channel is the bottom one.
John Camella found that the object in the Crab Nebula was pulsating 30 times a second. A star of the most compact type already known, a white dwarf, could not perform so rapidly. The Arecibo astronomers also found that this pulsar was perceptibly slowing down. The discovery gave a great fillip to the theory that pulsars represented a completely new state of matter, a star crushed to the fantastic density of an atomic nucleus, a neutron star. For a year, radio telescopes were discovering new pulsars at an average rate of one every 2 weeks. But all through 1968, optical astronomers tried in vain with giant telescopes to detect any visible pulses. One cloudy night, early in 1969, a small telescope at the University of Arizona's Stewart Observatory scoops the first visible pulsar. Two men who have never used the telescope before, John Koch, an American, and an Englishman, Michael Disney, spot the pulsar in the Crab Nebula. The leader of the team, Donald Taylor, was absent that night. By accident, the astronomers left a microphone switched into their tape recorder, thus preserving an unprecedented record of discovery. What you see is reconstructed. What you hear is the astronomers' actual conversation at the historic moment.
It's growing. That's it. My God, we got it. That's a bleeding pulse.
It is, isn't it?
God. But that's a bloody good pulse. It's to me.
It is, isn't it?
God, go on, just come and look at it down here.
Perfect. Right. Yeah, yeah. Well,
that's a bloody pulse, isn't it?
Yeah.
God damn. God, fantastic. That's a bloody pulsar.
This is a historic moment.
I hope it's a historic moment. What?
This is dropping. It's been up around 700.
The flashes, 30 times a second, match the radio pulses exactly. One theorist who's always insisted that only the highly crushed neutron stars can explain the phenomenal pulsars is Tommy Gold.
What I think happens is about like this. The magnetic field of the star acts like the spokes of a wheel with the neutron star itself at the hub. Any gas that is flowing out of the star will be forced to flow out along the spokes of this wheel. Now, the neutron star can rotate remarkably fast. It could spin about as fast as 1,000 times per second. Therefore, it is not very far from the neutron star itself that the spokes are whizzing around at almost the speed of light. Any gas caught on them will therefore be accelerated to these very high speeds. Now we understand that high-speed gas moving in this way will radiate, both in the radio band and visible light. And both of these have been seen from the pulsars. The way that the pulses are generated is, I think, in the manner of the light from a lighthouse beacon, where the shaft rotates and the beam of light swings around and causes pulses to be seen by an observer.
You can use a so-called neutron star as the center of your model for the pulsars. But for a nuclear physicist, the question is, how do you get a neutron star to operate? We don't know enough nuclear physics.
For Willie Fowler and other experts, the idea that pulsars are neutron stars is a source of excitement and controversy. Here we're at a gathering of leading astronomers from all over the world in Dallas, Texas. There is plenty to argue about. One of the visitors comes from Moscow, Joseph Shklovsky. Jeffrey Burbage is an English-born astronomer, now at San Diego.
Physics is uncertain. Even the nuclear physics is uncertain because the densities are several times what we can observe in actual nuclei. In fact, they can be 10 times as much.
There must be neutron stars. And last year in Cambridge, you were writing a paper that said there could not be neutron stars.
I never finished it, John. I never finished it. They've caught up with me.
No, but you always have to go this way. But the point is that it's got rotation in it, and therefore what you're really looking at is something which was formed in a rotating medium. So if you take a large object collapsing that rotates enough, then you go back to the old argument that we had, that maybe it breaks up.
How can you be sure that the residue of a violent explosion, for example, is a neutron star? Perhaps it's a white dwarf. Perhaps the residue doesn't get to the densities that are necessary for a neutron star.
So what's happening with the Ariel now?
Well, we just
The girl who started all the fuss about the pulsars, Jocelyn Bell, was a research student at Cambridge, England.
And look more closely over a further area.
She's now married and revisiting her former teacher, Anthony Hewish, at the Mullard Observatory, where she first noticed unexpected pulses from the sky in August 1967. When they reappeared that November, Hewish led the all-successful investigation.
I think now they are, Tony, because when I left, it looked as if they were going to be white dwarfs of some sort. That was October.
Well, the interesting thing is that John Camella at Arecibo has picked up this Crab Nebula pulsar flashing 30 times a second.
Yes, that's fast.
It's very fast. In fact, it's flashing so fast that it would fly to pieces if it was a white dwarf. So I think we can forget all about the white dwarfs and concentrate on the neutron stars.
And are neutron stars going to satisfy all the other peculiar things, all the other peculiar properties?
Well, it's going to be a bit of an uphill slog for the theoreticians. This is the first real evidence that neutron stars exist.
The Crab Nebula has yielded its greatest secret. Since the discovery by the Stewart Observatory, we now know that at the heart of the cloud, a star long known in photographs is flashing 30 times a second. It is the one in the middle of the circle, the most astonishing star ever discovered. And there, at this moment in astronomy, the mystery rests.
As your bright and tiny spark lights the traveler in the dark, though I know not what you are, twinkle, twinkle, little star.
Such progress with pulsars in a matter of months is a remarkable success story for astronomers. The latest score is about 36 pulsars discovered. Astronomers dearly wish they could have made as good progress with even more astonishing objects. A profound mystery for 6 years, the quasars. And that's what we'll turn to next. It will take us out into the depths of the universe. The pulsars lie among the stars of our own galaxy, the Milky Way. The quasars are much farther away, out in the realm of the other galaxies. The galaxies are vast collections of stars that lie scattered in space and time, millions of light years, hundreds of thousands of millions of light years away. In other words, our telescopes are time machines. The light from distant galaxies has taken so long to reach us that we see the universe as it was billions of years ago. The farthest or oldest objects astronomers can see are quasars. They're visible across such great distances because they're unbelievably bright, much brighter than galaxies. Yet they're also much smaller than galaxies and look very like stars. They're quasi-stellar, star-like in appearance, which is why they're called quasars. They're perhaps the most violent events to be seen in the universe. But before we embark in earnest on that story and its implications, we're going to take time out for the next 10 minutes simply to accompany one of the great astronomers of our time as he goes to work at Palomar in the hills of California. A young Dutch astronomer was the first man to grasp the fantastic power of the quasars. 6 years later, he continues to investigate them. He's taken leave of his family to spend 4 nights at the telescope. Martin Schmidt.
I got interested in astronomy when I was about 12 years old. I have an uncle who is an amateur astronomer, and it was, I think, in 1942 that he showed me his telescope and a few objects like the moon, double stars, and a few planets. He told me at the time that I could construct my own telescope by using 2 lenses, one with a long focal length, one with a short focal length, and mounting them in a tube. When I came back from the holidays, I did that, and I wrote him, said, build this little telescope, and what should I do with it? He then advised me to buy a little book about things you could see in the sky, and this is really how I got started in astronomy. As an amateur astronomer, I had never a telescope that was larger than 2.4 inches. Obviously, this is quite a change, and it is certainly a privilege to be able to use the largest telescope that exists.
Martin Schmidt is one of only 16 astronomers in the world who are privileged to use the 200-inch telescope regularly. Others may be admitted as temporary visitors. For 20 years, the Palomar telescope has been the sharpest eye on the universe.
I remember when I came into the 200-inch dome for the first time, some 10 or 12 years ago, that I was deeply impressed with the telescope, and I stood in awe, looking up for about 5 minutes. Now when I come in, I come out of the elevator door, I go to the Cassegrain observing cage, and I now realize that I sometimes don't even check whether the telescope is there or not. Well, the weather looks fairly good tonight. I'll give you the coordinates of the objects as they come along, and I think we'll start on a number of 4C objects.
4C?
Yeah.
Okay, fine.
The 4C objects that Schmidt is to investigate tonight are visible quasars listed in the 4th Cambridge Catalogue of Radio Sources. He will work in a cage behind the glass, 35 tons of it, that forms the mirror of the telescope, 200 inches in diameter.
Not all my colleagues wear a helmet in this cage, but they usually come out bloody.
Schmidt is loading the camera. It'll record a smear of light from 8,000 million light years away at the edge of the visible universe. The cage contains electronic equipment. It greatly speeds up the work of the telescope by registering faint light more quickly. It cuts the exposure time for a photograph from hours to minutes. But the equipment is heavy. That's why it has to be mounted in this position, right behind the mirror, to disturb as little as possible the delicate balance of the great telescope as it swings on its mounting.
Gary?
Let's go to 4C 25.5.
4C 25.5.
124.58
124.58
plus 25.49.11.
plus 25, 45, 11.
49.11.
49.11.
Right.
You ready?
Yep.
Even for Martin Schmidt, the ration of time on the telescope is only about 30 nights a year. He wastes no time. Astronomy is an art as well as a science. The observational astronomer stakes his reputation on his performance at the telescope.
Gary?
Yes, Martin?
Let's get started on this one. 10 minutes, please.
Fine, and you got away at 6:36.
Okay.
Skill as an observer is a matter of judging how to make the best possible use of complex and expensive equipment and how to interpret the results it yields.
Let me give you the data for this.
Fine, ready.
The grating is 26. Angle 3130.
Grating 26, angle
31 degrees, 30 knots.
Slit 8/80.
Slit 8/80.
Plate 2AO.
Plate 2AO.
I'll get you the seeing later on.
Fine, thank you.
The great telescope is working uncomfortably close to the limits of its performance.
This work requires concentration. Scene looks pretty good tonight.
No?
I think it's about 3.
3.
The astronomer must watch, lest seeing conditions should worsen tonight, obscuring features and light that's traveled since before the Earth was formed.
Gary?
Yes?
Would you get me some music, please?
KFAC?
Yes, please.
Just a moment.
look how the floor of heaven is thick inlaid with patines of bright gold. There's not the smallest orb which thou behold'st, but in his motion like an angel sings, still choiring to the young-eyed cherubims. Such harmony is in immortal souls, but whilst this muddy vesture of decay doth grossly close it in, we cannot hear it.
On those 4 nights, Schmidt took 44 little photographs like this. The light of quasars broken up according to its wavelengths. Behind me, you can see what's revealed on this tiny plate when seen under a powerful magnifying glass. 6 years ago, such a spectrum was a turning point in astronomy. Schmidt obtained it from a quasar, first pinpointed by radio astronomers in Parkes, Australia. Schmidt puzzled over the spectrum for 6 weeks. It made no sense. Then, on February 5th, 1963, he understood. He recognized a group of lines, but they were completely shifted to the red end of the spectrum.
That night, I went home in a state of disbelief. I said to my wife, "It's horrible. Something incredible happened today."
Let's see roughly why Schmidt was so shocked and what his spectrum meant. Imagine a bright source of light which is moving rapidly away from you. The light waves that it emits are stretched out. They're moved towards longer and therefore redder wavelengths. The faster the thing is moving away from you, the more red-shifted its spectral lines become. Astronomers are by now used to the conclusion that with the biggest reds, that is those which are moving fastest away from us, also the most distant galaxies. It turned out the faster a galaxy is receding from us, the swifter, the more distant it is. Now, with this information, it's possible to show roughly what Schmidt found. Schmidt's quasar spectrum is this middle spectrum. The upper and lower spectra are comparison laboratory spectra. Schmidt recognized a pattern of 3 lines due to atomic hydrogen. But these 3 lines were not in their usual place in the spectrum. Their usual place is somewhere over here. They had been red-shifted by this very large distance. The amount of the redshift corresponds to a velocity of about 30,000 miles per second. And such an enormous velocity means that the quasar must be very far away. In fact, that it must be about 1 billion light years from the Earth. Now, how is it possible that an object which appears to us so bright could be so far away? A huge mass of gas or stars falling together might conceivably produce such a large amount of energy, enough to drive a quasar. But there's a problem with this idea. It's that gravity is, in a sense, too strong. There's nothing to stop the collapse of such a mass of gas or stars. It would continue to collapse. It would pass through the neutron star stage that we talked about before, and eventually its gravity would become so intense that even light would be unable to escape from the object. Therefore, the object would turn off it would disappear. It would vanish from the universe, leaving behind only a sort of black hole of gravity, a little like the grin on the Cheshire Cat. The universe may in fact be riddled with such black holes. Imagine a spaceship wandering around, minding its own business, encountering such a black hole. What happens to it? Well, it must vanish. It must disappear from the universe. There are some who believe that matter which disappears down such a black hole must reemerge at some other point in space, at some other epoch in time. This may be just a sort of highbrow science fiction, or it may really be true. The quasars are such a puzzling phenomenon that they may really lead us to revise our notion of the laws of nature. It wouldn't be the first time that astronomy has taught physicists something new. But it does seem clear that simple common sense notions about the universe are just totally inadequate to account for such an extraordinary phenomenon as a quasar.
Quasars are some kind of immense explosion far away in space and time. For one point of view on them, we can turn to the radio astronomers, whose radio telescopes pick up strange radio noise. Our forefathers imagined that the heavens were filled with the music of the spheres and choirs of angels. Instead, what we hear when we convert the radio signals to sound is this hiss, like escaping steam. It brought the first news of violent upheavals in the distant universe. At Cambridge, 3 dishes, one of them movable, make up the ingenious 1-mile radio telescope. Records are obtained day by day with the movable dish in different positions along its railroad track. Combination of these records produces maps of the radio sky as detailed and precise as you'd obtain if you had one huge dish, a mile in diameter. There's no one around in the control room of this great telescope. It works automatically and unattended. For its patient exploration of the sources of radio noise in the universe, it's controlled by a computer. But what is it picking up out of the sky? Some radio sources are the remains of exploded stars, but others, much farther away, turn out to be exploding galaxies. Imagine a huge assembly of stars like our own Milky Way, ravaged by a central explosion far more violent than a supernova. If it happened in the Milky Way, it would wipe out all life throughout the galaxy. Such galaxies broadcast their distress by strong radio emissions across many millions of light years of space to the dishes of the telescope. The instrument reveals the shapes of the regions in and around the galaxies which are emitting strong radio waves. Those shapes tell remarkable stories of past explosions, as Anthony Hewish explains.
This is a typical radio galaxy. Just here, optical telescopes show a visible galaxy. These clouds on either side of it, which are broadcasting radio noise, are huge puffs of atomic particles wrapped in magnetic fields. We think they've been ejected by a mighty explosion in the heart of the galaxy. This pattern and the radio power are quite different from those of a normal galaxy, like this nearby spiral in Andromeda. Here, the weak radio emission matches the visible shape very closely. Sometimes it's obvious from the photograph that a galaxy is in distress. See the blobby, bright blue jet shooting out here. This galaxy is also a strong radio source, but the double cloud has not yet clearly developed. A galaxy can explode more than once. This one, mapped by radio astronomers in Australia, has a repeated double form, corresponding to one explosion long ago, with the gas clouds now stretching far across the sky, and another, much more recent, where the gas clouds are still close to the visible object. In this case, the galaxy is obscured from view in visible light, but the radio maps we've made in Cambridge suggest that it's been racked by explosions several times, like a machine gun swiveling as it fires. When we calculate the energy tied up in these radio clouds, it's amazingly large. It's as if the total energy supply of many millions of stars has been stolen and converted into high-energy atomic particles swirling in huge drifts of magnetic field. This mystery was unfolded in the early 1960s by the discovery of quasars, or quasi-stellar radio sources. These are so compact they look just like stars in both optical and radio telescopes, yet they give off more energy than a complete galaxy. But here, a star-like visible object, optically a quasar, 3,000 million light-years away, looks in our radio telescope like a typical radio galaxy. A growing number of astronomers think that quasars and radio galaxies are directly linked, roughly according to this sketch diagram here. We believe that an explosion right inside a galaxy is the visible quasar, and that this explosion throws out clouds of atomic particles, which we later observe as a radio galaxy. By studying the radio maps, we can hope to follow the evolution of this explosion, but we cannot, of course, say why galaxies explode or what causes the vast release of energy.
The nature of quasar explosions baffles the world's astronomers. It's as if many millions of stars concentrated in a volume little bigger than our solar system. Yet according to present knowledge of the forces of nature, no such concentration of matter could survive in a visible form. So quasar watching is now the first priority for the world's biggest telescopes, like the 120-inch telescope at the Lick Observatory in California. Tom Kinman is an expert on quasars, and what he's going to do tonight is measure the brightness of a quasar by comparison with nearby stars. It's hard to see anything of these little pinpoints of light unimaginably far away in space. Beside the red shift, the most striking feature of some quasars is the way they vary in brightness.
Okay, could you open the mirror, please? All right.
The 120-inch mirror of the Lick telescope will focus the starlight to the cage where Kinman rides. This position is known as prime focus. Here, nothing stands between the big reflector and the astronomer's instruments. What staggers Kinman is that some quasars double in brightness from one night to the next. Such flashy behavior implies great violence. It also tells of extremely concentrated centers of activity in quasars. If they were big, they could not change so fast.
All right, centered now, thank you. Thank you. Right, I'll do yellow filter first.
Y star, C6 filter.
Right, yellow filter start.
We can see the outcome of this work in a striking way. A smaller telescope at Lick, checked with this big one, has provided our program with data for a motion picture. It shows, greatly speeded up, how the quasar called 3C345 changes in brightness in the course of a year. Every few months it doubles in brightness in a matter of days, and as quickly declines again. At Parkes in Australia, the hunt for new quasars goes on. When the telescope has pinpointed a radio source, a computer prints a map that shows its position in relation to bright stars in that part of the sky. The crosses represent the stars. Over one of the photographs from the Palomar Observatory's sky survey fits the map drawn by the computer. In this way, the source detected by the radio telescope may be related to a visible object.
We have another quasar here.
This is John Bolton.
Just a single night's observation with the 210-foot telescope can give us 100 accurate positions of radio sources. And of these, as many as 40 will be newly discovered quasars. Radio galaxies and quasars have a lot in common, but we are beginning at last to distinguish between the two classes. We observe over a wide range of wavelengths, and we find that the quasars emit more strongly at the short wavelengths. In other words, their voices are higher pitched. Even more important, we've finally begun to find out something about the size and structure of the quasars, which appear to a simple telescope as mere points of light or radio waves. In order to do this, we need two radio telescopes separated by a long distance to form an interferometer.
The interferometer is just a combination of two spaced radio telescopes. In this case, the big one is stationary and the others moving along the railroad track. Both dishes are trained on the same radio source in order to measure its size. The pens show a wavy pattern. That's because signals from the radio source in the sky arrive at the two dishes, first in step, then out of step, then in step again, as the distance between the dishes increases. When they're in step, they produce a large combined signal. Out of step, the combined signal is smaller. This happens alternately and produces the wavy pattern that the astronomers call fringes. As the separation between the dishes increases, a striking thing happens. Just watch the pen on the left. The wavy pattern starts to shrink. What's happening is that the radio source is too big to give precisely matching signals at the two dishes when they're so far apart. The bigger the source, the sooner the pattern disappears as the dishes separate.
We've only got about a third of the signal we started out with now. $900 feet, Ben? The fringes have completely disappeared now. You can stop the track drive. We've lost the pattern with the dishes at this separation. All we have to do now is a simple sum, which tells us the diameter of the source.
For radio sources that look very small, like many quasars, the wavy pattern will not disappear with two dishes as close as this. The first hint that quasars existed came when Jodrell Bank in England found that for some radio sources the wavy pattern persisted, even when dishes were 100 miles apart. Canadian radio astronomers at the Algonquin Observatory have pioneered a technique which allows radio telescopes thousands of miles apart to work together. By this means, even small quasars are at last yielding the secret of their true size. The trick is to make tape recordings of radio signals reviewed from a quasar at the two dishes, but to time them extremely accurately with atomic clocks. The records can then be combined as accurately as if the telescopes were really much closer together. Canadian and American astronomers have made several such links, including transatlantic ones to Sweden and Jodrell Bank in England. The first long-distance link was between Algonquin and a radio dish on the other side of Canada 2 years ago. The latest and longest link is being attempted by the Canadians right now, between the big dish at Algonquin and the big dish at Parkes, Australia. This combination makes, in effect, a radio telescope as wide as the Earth. It will give new information on the shapes and sizes of quasars, and perhaps show whether quasars are indeed exploding galaxies. Hewish at Cambridge said he thought quasars and exploding galaxies are the same kind of event at different stages. John Bolton at Parkes said the quasars were higher pitched than radio galaxies, implying that they might be inherently different. But we've got other evidence from optical astronomers who can see a connection between galaxies and quasars. To tell us about that, here's Wallace Sargent at Palomar.
Galaxies are large, quasars are small, but really it isn't quite as simple as that. There are odd-looking galaxies called Seyfert galaxies. They have very bright centers. This picture of a Seyfert galaxy was taken with a long exposure. But if the exposure is significantly reduced, a star-like object sitting at the center is all that registers. It is this center that resembles a quasar, but it is 1,000 times less bright. This is the first Seyfert galaxy, which was discovered 50 years ago. In the last few years, more distant galaxies with bright centers have been discovered. This one, called 1 Zwicky 1, is the brightest galaxy known. Its center is 100,000 million times brighter than our sun. I have suggested that this object is really the missing link between galaxies and quasars. Then there are groups of galaxies in which one of them seems to be ejected with enormous energy from the rest. We call this Stephan's Quintet, and we've known about this bunch for all of 8 years. Here's a remarkable chain of compact galaxies. 4 of them are traveling together. But in 1968, I found that this one is moving away from the others at a speed of at least 15,000 miles a second. What can have happened here except some tremendous explosion? Clearly, there's something odd going on here. Either we need a new source of energy, or the familiar sources are working in ways that we haven't yet discovered. The sun and the stars generate their energy by thermonuclear reactions. But this source isn't powerful enough for the quasars. We have to think again.
On an airfield near San Francisco, astronomers prepare a telescope for flight. Here's another way to peep through the curtain of the Earth's atmosphere that cuts off most of the radiation from the universe. The telescope rides into the stratosphere in a converted businessman's jet. It's for picking up previously undetected rays coming from distant galaxies, a gold-plated telescope. In the hangar, a pioneer of infrared astronomy, Frank Lowe, of the universities of Arizona and Rice, makes ready the telescope's special detector. He has to cool it to an extremely low temperature, just 2 degrees above absolute cold. That's what he's doing here with liquid helium. Lowe wants to detect heat rays, faint infrared rays coming from far away in the universe. The warmth of his detector would swamp any such rays if he didn't make it as cold as possible. Heat is one enemy, water vapor in the air is another. Infrared rays journeying from millions of years from distant galaxies are wiped out at the last moment as they near the ground. The telescope has to go 10 miles up to get above the layer called the tropopause, where the moist air of the Earth's surface gives way to the dry air of the stratosphere. In its jacket of liquid helium, the detector fits on the telescope. The heart of the detector is a germanium crystal that is very sensitive to infrared rays.
Martin, how high do you think we'll get above the tropopause today?
Well, Frank, we're figuring on going to 50. Well, that'd be about 4,500 feet above the trope, I think, today.
The infrared galaxies that Lowe is investigating are the very same bright-centered galaxies, the Seyfert galaxies, that Wallace Sargent spoke about just now. But these galaxies generate more heat than light. Some of these heat rays do reach the ground, but are even stronger at wavelengths wholly blocked by the Earth's lower atmosphere. So, Lowe's telescope is carried 10 miles high.
Okay, we're at 50,000 feet now. We're going to go ahead and start our observation.
Roger.
Okay, Frank, this is Ron. We're level at 50,000. How's this heading look? We're headed 180 degrees now. Do you see the star?
No, not yet. Could we have 2 degrees more to the left?
Okay, understand. 2 degrees to the left. Stand by. Okay, rolling out. This is 2 degrees to the left now. How's that look?
Ah, there it is. I see it. I have the guide star. I'm putting it on now. Pull this heading steady. We'll start observations.
Okay, very good.
All right, here's the positive deflection. Holding that. Here's a negative deflection.
Frank Lowe testifies that heat rays from these few special galaxies equal in energy all the light from all the stars in the universe. This discovery bears out Wallace Sargent's opinion that we have to think again about the forces of nature.
Okay, these data are being taken on gain 4-6. Repeat, gain.
The infrared is just one of the new windows now opening on the universe. If you had infrared eyes, here's how the sky would look. These are cool stars, or stars not quite formed. This is a bit of the sky towards the center of the Milky Way, itself a source of infrared rays. Here's how it looks by visible light. Until recently, this was the only window on the sky. Radio telescopes give quite a different picture. The ordinary stars, other than the sun, just aren't seen. Instead, violent events are picked up. Exploded stars and galaxies, pulsars, quasars. Visible light and short radio waves and some infrared are the only signals that pass unhindered through the atmosphere. Spaceflight opens up a range of new windows. As we saw earlier, with ultraviolet eyes, you'd pick out the very hot stars. And now rocket astronomers have found X-ray stars, a group of them in our same patch of sky. They're a new mystery for the astronomer. Here's the very latest window, opened by American scientists last year, using a satellite to pick up gamma rays, which are like very energetic X-rays. So far, they just show rough blocks of brightness in the Milky Way, particularly the center of our galaxy.
We should keep an eye on this part of the Milky Way, towards the center of our galaxy. Some strange things are happening there. Not only is it a source of gamma rays, but it's also an intense source of infrared radiation, as these contour maps imply. Dutch radio astronomers have found clouds of gas rushing outwards at high speed from the center of our galaxy. They imply that there was a violent event, an explosion at the center of our galaxy some 30 million years ago. It wasn't an explosion as violent as in a quasar. If it had been, we wouldn't be here today. It was just a sort of tremor.
Now we must move on to the biggest question of all, the origin and fate of the universe itself. In this connection, too, there have been astonishing discoveries just in the past few years. Are we yet smart enough to tell a true story of the universe? Men have tried to do so for centuries in various ways. According to the book of Genesis, God made the sun, the moon, and the stars to give light to the earth. He set them in the firmament of heaven. To the ancient world, the firmament of heaven meant the solid dome of the sky in which, they thought, the stars were fixed. And if a man could only look beyond the vault of heaven, he might see the cogs and flywheels that made the great dome revolve in the night. The ancient Egyptians identified the earth with the reclining god Teb. The god Shu was in the air, and reaching up to the sky, the strapping goddess Nut. In India, the Hindus pictured the earth as a sort of water lily with leaves for continents. The lotus flower was Meru, the abode of the gods. Around this, the sun and stars revolved. For Jews and Christians, too, the flat earth floated. God created Adam and Eve, and the ocean lay all around. Even as the lessons of the ancient Greeks and of the new explorers sank in, that the earth was not flat but round, they still saw the earth as the center of the universe, surrounded by the spheres carrying the heavenly bodies. And though man saw himself at the center of all things, it was a lowly place he occupied, way down in the hierarchy of archangels and six-winged seraphs. Tycho the Dane, 4 centuries ago, was the founder of modern astronomy, but he clung to the view that the Earth was the center of the universe. In Tycho's cosmos, the sun still orbited Earth, but the other planets went round the sun. He rejected the system of the Polish monk Copernicus, in which all the planets were put in orbit round the sun. The muse of astronomy, for a brief period at least, gave greater weight to Tycho's universe. But the very ancient view that everything in the cosmos revolved around us had at last been discarded once and for all. The 2nd century astronomer Ptolemy, who'd crystallized that view of things, fell right out of favor. In his words, erigor dum corrigor, or in the modern idiom, back to the drawing board. But the muse didn't favor Tycho's system very long. She heard about the Italian Galileo, his use of the telescope, and the quite novel view of the universe it provided. And in England, Isaac Newton discovered the law of gravity, the force that rules the universe. The Copernican revolution prevailed. But old habits of thoughts die hard. The sun simply replaced the Earth as the center of the universe. Throughout the 18th and 19th centuries, ideas about the universe and our place in it remain very conservative. Only in the lifetime of some astronomers still alive today has it been revealed that our sun is not the center of the universe, not even at the center of our galaxy, but some way out from the center in the suburbs. Only in the 20th century have men grasped the scale of the universe, with its population of galaxies disappearing in a vast volume of space.
Scientists narrowed down the mystery of creation. All that seems to be necessary is some gas at the beginning. We understand how hydrogen condenses into a furnace of stars, how these stars cook heavier elements in their interiors, how these heavy elements are spewed out in supernova and other explosions to enrich the interstellar medium, and how subsequent generations of stars and planets form from the hydrogen and the heavier elements. If in the laboratory we duplicate a primitive planetary atmosphere and supply it with some energy, what is produced are organic molecules quite like the ones which make us up. It's an extraordinary thing. It's as if the origin of life is in the cards, as if it's a forced process of physics and chemistry. And we understand, at least in principle, how from these humble beginnings life could evolve to produce wondering men who ponder how it all came about. And we must not think that we are the pinnacle of creation, the end product of cosmic evolution. It may well be that elsewhere there are creatures more advanced than we. While there is some uncertainty about many of the steps in this grand picture, the overall pattern is agreed to by most scientists. And yet there's the beguiling problem, where did the original hydrogen come from? We've talked about exploding stars and exploding galaxies. In the Big Bang theory, we're living in an exploding universe. In the Big Bang theory, the universe began some 10 billion years ago. It was instantaneously created. All the matter and energy in it were produced somehow from nothing. As the primeval gas cloud expanded and cooled, there were condensations in it, condensations which evolved to produce galaxies, not all of them spirals. The subsequent evolution in the Big Bang theory takes many forms. In some of them, the galaxies expand from each other forever. In others, they slow down and contract, and there's a sequence of Big Bangs. In the Big Bang theory, there's no mystery about the recession of the galaxies. It's no more mysterious than the expansion of the fragments of a bomb explosion. In the steady state hypothesis, the universe has no beginning and no end and no outer boundary. There's no quarrel in Hoyle's view with the expansion of the universe. Galaxies recede to a distant horizon, but their place is taken with other galaxies newly formed from the intergalactic gas. As more and more generations of galaxies are produced, perhaps you think that the intergalactic gas should be used up. This is not the case because in the steady state theory, new gas is produced all the time from nothing. And how is it produced? It's produced in just the same way that in the Big Bang theory, matter is made from nothing.
Although they sound completely different, a decision between these two types of theories has been far from easy. As we said earlier, our telescopes are time machines. So great are the distances in the universe, and so long is the journey made by light and radio waves from distant sources, that we can see the universe as it was when it was far younger. If the steady-state theory is right, the distant, younger universe should look little different from the nearby regions. If the Big Bang story is correct, then we should see evidence of change. That's one way of trying to choose between Big Bang and steady state. The other way is to look for evidence of the Big Bang itself. If there was a great fireball, the universe was then very hot and filled with X-rays and gamma rays, like those generated in the fireball of an H-bomb. By now, though, the universe has cooled down, and that radiation has lost energy. It's become short radio waves. Your own television set is a crude sort of radio telescope, and some of the snow, the unavoidable flecks of light you see on it, is radio noise coming from the universe. According to some astronomers, part of the snow comes from the fireball of the Big Bang itself, from the creation of the universe. Static is a matter of practical concern to radio engineers like those of Bell Telephone Laboratories in Humdel, New Jersey. It was here they picked up the first hint of an echo from the Big Bang. In 1965, communications satellites were the great novelty in the telephone industry. Remember Telstar? This horn was built for those experiments. It's unusually sensitive. And like Frank Lowe's airborne telescope, its radio receiver is cooled with liquid helium. It's designed for very short radio waves, microwaves they're called. But Arno Penzias and Robert Wilson of Bell Laboratories thought something had gone wrong with it when they picked up unexpected radiation. They took it apart and rebuilt it. Arno Penzias tells what happened.
When the horn was looking slantwise through the atmosphere, we picked up radiation from the air as we expected. As we looked higher, the intensity dropped, but we were left with a small amount of additional radiation which we could not explain. It seemed to be coming from somewhere outside the atmosphere. No matter when we looked, day or night, winter or summer, this background of radiation appeared everywhere in the sky. It was not tied to our galaxy or any other known source of radio waves. It was rather as if the whole universe had been warmed up to a temperature about 3 degrees above absolute zero. We were surprised to learn that Bob Dickey at Princeton had predicted just such an effect from the Big Bang.
In fact, Robert Dickey was making preparations here at Princeton to look for just such fireball radiation when the news came from Bell Laboratories. He'd worked out what should be left today of the fierce radiation from the fireball of the Big Bang, if that's how the universe began. It would still be around, but cooled to a background whisper of radio waves.
And the other... Hi, Bob. Good to see you. I was talking about the black body radiation.
Well, yeah, familiar curve.
Yes, we've seen it many times.
Anything new?
No, nothing new.
The Princeton scientists, including David Wilkinson here, promptly set out to try to prove that the newly discovered radio background really came from the Big Bang.
The nice thing about Dickey's theory is that it makes two very specific predictions about what one would expect. One is that if we're here on the Earth and we make measurements with our radio antennas in all directions, in fact, we should see the same intensity no matter which way we look in space. This experiment was done here in Princeton by Professor Partridge and myself, and it really seems to be true that no matter which direction you look out into space, you see the same intensity of this fireball. So the theory fits very nicely there. The other prediction that Dickey's theory makes is that all of the measurements of the intensity of this radiation should fit on a very specific curve called the black body curve. The first measurement was done by Penzias and Wilson and fit on the curve about there. In fact, that measurement fixes the curve. After that measurement, all of the other measurements should fit on this curve. The next one was made here in Princeton by Professor Roll and myself. Seemed to fit very nicely on a curve which corresponds to a temperature of 3 degrees Kelvin.
Blackbody radiation just means the strongest radiation that anything can emit by virtue of heat. Its strength at each wavelength depends on the temperature. If the Big Bang story is right, the temperature of the universe must always read 3 degrees above absolute cold. But the strongest radiation comes at a tricky wavelength of 1 millimeter, which ground-based detectors can't reach. At the Naval Research Laboratory in Washington, D.C., a rocket scientist has ventured to take the temperature of the universe near that wavelength of 1 millimeter. He's checking a telescope he's flown above the atmosphere as a cosmic thermometer.
We have a black body temperature of about 6 degrees.
Kandia Shivanandan and his colleagues at Cornell University obtain a result not fitting that 3 degrees black body curve.
However, just recently, there's been a new measurement by a group at Naval Research Laboratories and at Cornell University at higher frequencies, frequencies that are over this peak, and they seem to find a very high intensity. In fact, they find an intensity that comes way up here, well above the black body curve. In fact, about 100 times more intense than would be predicted by this curve. However, one needs more measurements here, but they do seem to be rocking the boat a little.
It's a hard measure to get right, and Shivanandan's result clashes with other indirect evidence about the temperature of the universe at that difficult wavelength. Here at Cambridge, besides the alleged fireball radiation, there's a further view of cosmic history. The radio astronomers at Cambridge have had many successes, including the pulsars. But their leader, Sir Martin Royal, has always hoped to draw an overall picture of the universe, from the way the distant radio galaxies and quasars appear scattered in space. Now he thinks he has it.
Successive sky surveys which we have made here at Cambridge point to only one conclusion. The universe has changed and is still changing. From our census of the faintest and most distant objects, we can say something about the nature of the universe as it was several thousand million years ago. Quasars and exploding galaxies were commoner then and more crowded together than they are now. What's more, at a distance of some 8,000 million light years, the number of radio sources falls off sharply. It looks as though there was a horizon of time when the galaxies were first being formed from primeval gas clouds following the Big Bang. Even with more powerful radio telescopes, I don't think there'll be much to see beyond, except the microwave background of the Big Bang itself. It seems that with our deepest Cambridge survey, we may already be spanning the entire history of the universe of galaxies.
On the future of the universe, Alan Sandage has a point of view. This American astronomer normally uses the 200-inch Palomar telescope. But at the moment he's in Australia, taking pictures of the nearest galaxies visible only in the southern sky, with Mount Stromlo Observatory's smallest telescope. He compares them with farther galaxies seen in the 200-inch. He also uses the big 74-inch telescope to check his ideas about the future of the universe.
I think the universe is slowing down. In fact, it is slowing down so fast that sometime in the future, the expansion of the galaxies will cease and contraction begin. The evidence comes from observations of the redshifts, the rate of recession or the speed of distant galaxies. Calculation shows that the time in the future is about 30,000 million years when all of the galaxies will have come to rest, after which contraction which nothing can stop, will begin. The galaxies will coalesce with one another and finally emerge once again into a new primeval fireball. What happens after this, of course, we don't know. We don't know if the universe will bounce. Will matter come again out of the primeval fireball, new galaxies form, the expansion again decelerate, collapse again take place, another death and another resurrection again out of another fireball?
There's a snag. There are not nearly enough visible galaxies to exert the mutual gravitation needed to arrest them in their tracks and drag them together again. Jan Oort, Dean of Dutch Astronomers, runs a radio observatory at Dwingeloo. His colleague, Ad Hosbas, is investigating clouds of gas approaching our galaxy. These astronomers have spotted a dozen clouds, each 10,000 times more massive than the Sun, moving towards us at up to 100 miles a second. Oort is interested in the cosmic significance of these clouds.
The interpretation of this phenomenon has up to the present been quite an enigma, but we think now that it indicates that matter is flowing into the galaxy from the surrounding universe. This matter, this gas, a kind of intergalactic wind, interacts with the gas already present in our own galaxy and so gives rise to the clouds that we observe. The amount of inflow gives some indication of the general density of matter in the universe. And it turns out that this general density is of the order of what one calls the critical density, at which a universe could just expand indefinitely.
In other words, this infalling gas means there's at least 10 times more matter in the universe than we can see in the forms of stars and galaxies. But it's still not enough to bring about the collapse of the universe that Alan Sandage predicts. Is there still more to be found? Rocket scientist Richard Henry at the Naval Research Laboratory testifies to much more invisible matter in between the galaxies.
Previous attempts to detect gas in the vast, apparently empty spaces between the galaxies have been inconclusive. We feel this is because people were looking for the wrong sort of thing. We think this gas is very, very hot indeed. At temperatures of hundreds of thousands of degrees, the only way to detect this gas is through the soft X radiation which it emits. We interpret the observations of Boyer, of B.G. Wilson, and of ourselves as indicating the existence of such a hot, thin gas. Now, this gas would be very thin indeed. Material less than that in a grain of sand would fill a volume larger than that of the Earth. Nonetheless, the spaces between the galaxies are so vast that this material could add up to more than 90% of all the material in the universe. Well, needless to say, so much additional material in the universe would have a very substantial effect on the future evolution of the universe and on its ultimate fate.
100 times more matter? That would be quite enough to halt the galaxies in their tracks and make the heavens fall, as Sandage promises. Back in England, we turn to other possible clues about the history of the universe. Here lives the Astronomer Royal. The Royal Greenwich Observatory no longer sits on its own zero of longitude by the River Thames. Driven out by the lights and smoke of London, it's renewed itself at Hurstmonceux in Sussex. Turned on the oldest stars, a new 98-inch telescope discloses the early history of chemical elements in the universe. Did a Big Bang or the quasars, the little bangs, play any part in forming them? Engaged in this stellar archaeology is Bernard Padgell.
With the telescope, we can see very old stars that were formed at a time when the galaxy was very young. I'm interested in studying the chemical composition of these stars, and from this type of work, there are two main conclusions that emerge. First, the amount of heavy elements is extremely small. Second, the small amount of heavy elements that we do see has much the same composition as the mixture of heavy elements that is found in young stars, or in the Earth for that matter. This result is really rather disappointing. We dig back into the remote past, hoping to find something different and primitive that perhaps will give us some idea of what cosmic material was like shortly after the Big Bang, if indeed the Big Bang actually occurred. What we find instead is simply a watered-down version of the situation that we have at present.
The present evidence for slowdown is consistent with all models of the Big Bang. This, however, is not really the reason that most astronomers believe Big Bang describes the real world. It is rather in the timing of the events which happened. From the observations of distances to galaxies, we can calculate the so-called Hubble constant, which gives the time in the past when the present expansion began. And this time, or this age, is 10,000 million years. There is yet another age, however, which is the time since the formation of the first stars in our own galaxy. We know that this occurred also 10,000 million years ago. And yet again, calculations from the laws of radioactive decay show that the chemical elements had their birthday 10,000 million years ago. The agreement of these three timescales is precisely what is required if the Big Bang theory is correct. For me, the most persuasive evidence that steady state does not explain the facts is that timescales all agree, and this could only happen if something like a creation event occurred.
But Fred Hoyle is undismayed.
It's about 20 years now since the steady-state theory was first thought of. Over that 20 years, there have been quite a few claims that the theory was wrong from observers, but if this had really been demonstrated, you wouldn't have found everybody still talking about the theory 20 years after. It would have gone into limbo. It would have been dead and buried. The trouble is, the observers are working near the limits of what can be done, and there hasn't been any disproof that really drives the nail into the coffin. There have been lots of opportunities for this. There's an opportunity over the slowing down of the universe that Sandage mentioned. Here, by using the quasars, it would have been possible really to show the theory was wrong, but as soon as this was tried, it didn't work. The same thing has happened, in my view, with the radio sources, accounts of radio sources of Professor Ryle. The first few hundred certainly were against the theory, but the next 10,000 have gone in the direction of the theory, at least in my view they have. And again, with the microwave background, it looks to me like just the same story. In the beginning, I thought this was pretty bad for the theory when it was first discovered, but then it's been found that straightforward sources are emitters of high-frequency radio waves and far infrared on an enormous scale. So it's a completely open question today, I believe, as to whether this background really comes from the general universe or whether it comes from sources in the general manner of radio astronomy. So I think, to me, I'm impressed over 20 years by the failure to drive what I call a nail into the coffin of the theory. This begins to assume a considerable significance in my mind, together with the theoretical development, so that I suppose in sum, today, I'm more confident that the theory is right than I've ever been at any time in the past.
This mountain, Babo Kivari, is more than a shrine. For the Papago Indians of Arizona, it's the center of the universe. Around this crag, the sun and the stars revolve. They've long taught their children so, in song. And the Papagos hesitated before leasing a lesser sacred mountain, Kit Peak, to the men with long eyes. From MIT to this desert filled with legends comes Philip Morrison with a considered judgment on our tales of the universe.
The Papagos Indians held all this land for centuries. And if they wish to believe that that extraordinary mountain shaft was the axis of the universe, they have a case. Maybe we could disprove this case if they would listen to us, if their theological and philosophical preconceptions would allow them to hear all the evidence. We too have a case about the nature of the cosmos, if our preconceptions too are allowing us to see and hear all the evidence that's in. That question we never quite know. Not only have we seen farther and look less provincially than the Papagos did, we also have to consider that we look into time. If we're looking far away, thousands of millions of light years, we're looking back thousands of millions of years of time. We don't need telescopes to do that. We need only to look at the Earth, where we live. This flower is a product of last summer's growth. Faded by now, but its atoms took up their partnership a few months ago, some tenths of a year. My hand is another group of atoms, which will last, even the bones, at most a few tens of years. This rock, a piece of granite from the land, may have lasted a few 100 million years or 100 million years. Notice the range. From a tenth of a year, a month, we can see less than that, a day, to hundreds of millions of years. The Earth itself is only a few times older. The remarkable point is that all the galaxies that we see flying away to the depths of space seem only at most to be a few times older than the age of the oldest rocks on our Earth. A few 1,000 million years for the Earth, maybe 10 or 20,000 of million years for the galaxies. That's all the range we have. This is the most remarkable coincidence, in a way, in cosmology. And all that we've seen in the distant, with the distant channels that we open, goes to support that. That's what we have to explain. The two great contesting sets of ideas which explain this, the Big Bang and the steady state, do it this way. The Big Bang very naively says that's all the time there was. The Earth is about as old as the cosmos because everything began, in some sense, only a few thousands of million years ago. The steady state, more subtle, says this is a kind of average. Things begin all the time, but the things in our neighborhood begin about a few thousand million years ago. It's a much more sophisticated theory. But nowadays, the last few years have brought us evidence for the naive cosmology. For myself, I find it hard to accept the Big Bang theory. I would like to reject it. How can we believe such a naive theory that says within a finite time, only twice as long as the age of our Earth, the universe was vastly different from its present state, a white-hot ball? I much prefer Mr. Hoyle's more subtle, steady state. But I have to face the facts as a working physicist. The evidence mounts up, experiment after experiment, at least suggests that the clear predictions of the most naive theory, the Big Bang, are coming true. The steady state gets more complicated, modified, difficult to check. So I think if the next couple of years go as these have gone, we shall, for a generation or two, hold on to the most naive cosmology. And not unless a wiser, more experienced generation comes after us will we change it. Perhaps they will see that it, too, was a provincial preconception.
Nationwide distribution of the preceding program is a service of the Corporation for Public Broadcasting.